Let's get started with today's material. Well, last time we were looking at the different algebraic techniques to compute limits. So we did a couple of crazy ones. We did this one involving simplifying a complex fraction. And well, number 4, I'm going to skip it for now because we're going to get to see this again when we do the derivative. So let me skip this one, but rather I'm going to do number 5. And number 5, that's the limit of x minus 16 divided by the square root of x minus 4 as x approaches 16. Well, number 1, we need to check whether we have an indeterminate form. Otherwise, if we don't have an indeterminate form, we may need to look at numerical approaches, that is, making a table of values, or a graphic approach. Well, so number 1, let's do direct substitution and see how it works. So that's going to be 16 minus 16 divided by the square root of 16 minus 4, which in this case is 0. The square root of 16 is 4. Minus 4. So we have the 0 over 0 indeterminate form, which means this is good. This is good. We may go about the algebra. Alright, number 1. So we have radicals in the denominator, and well, in this case, there's nothing to expand. So we can simplify the integral. I mean the limit. Also, we don't have any rational, complex rational expressions, so we can, divide out, find a common denominator, simplify, and get rid of those factors that cause the troublesome 0 over 0. Factoring, well, it doesn't seem like we can factor it right away. Well, any ideas on what to do with this limit?
We open it in such a way that we get root x minus 4 into root x plus 4.
Do you mean like...
Yeah. Say a plus b and a minus b.
So by the conjugate, multiply by the conjugate, is that what you mean?
No. I'm saying could we open up, like could we make it a square minus b square? Like we could write root x plus 4.
Root x plus 4,
And root x into root x minus 4.
Okay, so that's where I'm going with this problem. So number 1, the long way, it would be to multiply by the conjugate, square root of x plus 4 over square root of x plus 4. And well, we already did one problem in which we used the conjugate. However, we are going to take a different strategy because, well, number 1, the conjugates usually take long to write and to simplify. Instead, like he mentioned, we're going to rewrite. We are going to factor the numerator. But wait a minute, how can we factor the numerator? Because we don't have any common factors between x and negative 16. And well, we're going to factor out the difference of squares that we have in the numerator. But wait a minute, that doesn't look like a difference of squares either. Well, the number 16 is a perfect square, but x is not a perfect square. But with the following trick, we're going to make it look like a difference of perfect squares. Do we all agree that x can be rewritten as the square root of x quantity squared? Yes, minus 16 over square root of x minus 4. And well, what do we have? A squared minus b squared. This is a difference of squares, and that's a plus b times a minus b. That's how we factor a difference of squares. And limit x approaches 16, that's going to be the square root of x minus 4, or rather plus 4 times the square root of x minus 4 over the square root of x minus 4. And in this case, we may divide out these two terms. And in fact, if you observe, those two factors that we're canceling are the ones that are causing trouble, the troublesome 0 over 0. After canceling these two factors, we can say that we're in a safe place. And that's square root of x plus 4. And at this point, we may go about square root of 16 plus 4 which is 4 plus 4, which equals to 8. Okay? All right. Let's look at the next example. And this is the next and last for this section. So in this case, they're asking us to prove that limit of absolute value of x over x does not exist. And well, they're giving us a hint. And the hint is pretty much to consider the definition of the absolute value function. In other words, well, here is in general, but in particular for our case, absolute value of x equals, on the one hand, negative x whenever x is a negative value, and x whenever x is greater than or equal to 0. That means that in this case, we will have to look at this limit from both sides, that is x approaching 0 from the left, or rather 8, because there's a little typo here, this should be x.
Can you not have a negative x instead of the absolute value?
Yes, and that will become positive in order to get all these positive values. Right? So, and well, we would have to also look at the limit on the right. So that is, let's take the limit x approaching 0 from the left, limit x approaching 0 from the right, that is absolute value of x over x, absolute value of x over x. Well, approaching from the left. Approaching from the left means for all values of x that are to the left of 0. That means negative values. This means that we will replace this absolute value of x with negative x. And we'll divide this out. This will be negative 1. On the other hand, when we analyze the limit from the right, that is from the right of, for all values of x to the right of 0, which means positive values, well, absolute value of x becomes positive x, and this limit is 1. Now, what's the limit of absolute value of x as x approaches, in this case plain vanilla 0, not from the left, not from the right? What's the limit?
It does not exist.
Does not exist. Why is that? Why is it that it doesn't exist?
I just have a question. Why or how do you get rid of the absolute value sign when you're evaluating the...
Oh yes, from the definition of absolute value of x, you know. So okay, and that's going to take us back to the graph of absolute value, which looks like it's the V shape. Okay, so for negative values of x, the absolute value bars turn them into positive by this absolute value bar. So in this case, it's negative x whenever x is negative. That is, this x less than 0 means x to the left of all the values, all the values to the left of 0, which is negative value. So that's why this, in this case, and let me highlight with these colors. This, oh, oops, no, that's not a highlighter. This becomes a negative x in this case, all right? And with the positive version of it, this becomes positive for x greater than 0 means positive, x less than 0 means negative. So that's how, from the definition of the absolute value of x, this becomes negative x and positive x respectively. Okay? All right. So there's one more example right here. I'd rather skip it and move on through continuity because we're a little behind here. So for section 2.5, continuity. Well, Let's consider the graph of this function. We don't know what f of x is explicitly. I mean, it's just some random graph that will illustrate pretty much every single kind of discontinuity. Well, a function is continuous if there are no interruptions at all. In other words, a function is continuous if you can draw its graph without having to lift your pencil, like the one I'm doing in green. I didn't lift my pencil at all, right? But in this case, what about this graph? Oh, I have to lift my pencil here so I can keep drawing it. I have to lift my pencil so I can keep drawing it. I have to lift my pencil to keep drawing, etc. Oh, right here as well. So this is not a continuous function. However, these discontinuities are of a specific kind, and we're going to list and name all kinds of discontinuities right here. So, for continuity, notice, let's first of all list all the discontinuities. Well, there is a discontinuity here at x equals to -5. There is another discontinuity here at x equals -2. Do we have another discontinuity of which value? 3 and 5, right? Okay, what kinds of discontinuities are each of them? Number one, the ones that involve going to infinity on one side or the other, or both, because of vertical asymptotes. These are called infinite discontinuities. In this case, notice in this case there's a jump. Whenever, if I wanted to keep drawing the graph, I have to lift my pencil, jump. These are called jump discontinuities. Sometimes we call them gaps. That's another way to call the jump discontinuities. And this one right here for x equals to 5, this is what we call removable discontinuities. And sometimes we call them holes. Okay? Well, how to identify them? How are they described symbolically? And how are these related, to the limits that we compute? Well, that's what we have on the next page. Well, so let's look at the definition of continuity. So a function f is continuous at a number a, whatever that value is, whenever the limit as x approaches that value a, it's exactly the same as the value obtained when we evaluate the function. And well, let's go back to the graph. You might remember we did an example of finding a limit versus evaluating a function. For example, let's focus on the number 5. So, what's the limit f of x approaches 5? What would be the limit? What is the y value being hit when we approach 5? 0. Now, what is f of 5? -3 is the point in the middle of nowhere. Again, the idea of a limit is what is the value that we are approaching to, versus evaluating a function is answers the question, what is the point we're stepping on when x equals whatever value, y equals that value. So these are two different things. Now, does the limit agree with the value of the function? So for this reason, this function is discontinuous at x equals 5, and this confirms the definition. In this case, the limit of the function has to be exactly the same as the value of the function in order to have a function to be continuous at this value. So, number one, f has to be defined, of course. Otherwise, if it's not defined, well, we have issues there in the domain. And the limit has to exist, right? And in this case, we need to consider as well both sides of the limit, which is what we did in the previous example. Right here, notice I considered the limit from the left, the limit from the right. On both sides, we're coming to the exact same y value, so the limit exists. And number three, well, that's pretty much the theorem here, the definition that the limit of the function has to be equal to the value of the function. They have to be the same. So again, describing the different discontinuities, removable discontinuity, and we already mentioned how it looks like a hole, and that happens when the limit is not equal to the value of the function. Wasn't that the case at x equals to 5 on the graph, which is what we did before? So in this case, the limit is not equal to the value of the function. So that's one example of a removable discontinuity. Let's describe the next kind of discontinuity. The next kind of discontinuity is the infinite discontinuity, and this kind of discontinuities we obtain when the graph goes to infinity. That is when we have vertical asymptotes, when we go to the positive infinity or to the negative infinity. And well, this happens when the limits from either side can be either plus or minus infinity, and we have a couple of examples over here. We have an example in which at x equals to negative 5, whether from the left or from the right, they're going to positive infinity. It doesn't matter if it goes to negative or positive if they go to different infinities on one side or the other. Also, for x equals to negative 2, we have this infinite discontinuity, because in particular the limit from the right is going to negative infinity. And the third type of discontinuity is the jump discontinuity, and well, it looks like a jump, or we also call them gaps as well. And that happens when both of the limits, both of the sided limits do not agree. And let's highlight this and let's see this in action on the graph. Let me go back to the graph. So the limits are not the same. That means let's see. What's this time? What's the limit of f of x as x approaches 3 from the left? What are we getting? What's the y value being hit? When? So negative 2. What about limit f of x, x approaches 3 from the right? Do the limits agree?
No.
So this confirms the jump discontinuity. Both limits coming from different directions do not agree to the same value. Let's do more examples about this. So let's determine where each of the following functions are discontinuous, and let's describe the type of discontinuity. Number one. So if we look at the domain of this function, we have trouble with it. Number one, the denominator cannot be 0. Alright? This means x minus 2 equals to 0, so x cannot be negative 2. So that's the value that we exclude from the domain of this function. However, we can further simplify this function by factoring. Okay, let's factor the trinomial in the numerator. Let's factor it using the double bubble method. So factors of -2 that add up to -1, -2 and +1, and see what happens here. And simply x plus 1. So we would get the graph of the linear function y equals x plus 1. However, with some damage here. All right. Okay. Suppose we didn't know, and we didn't know all this. Okay, let me cover. Suppose we were just given y equals to x plus 1. All right. That'll be the graph of the linear function with y-intercept at 1 and a slope of, yes.
That's like the positive 2, right?
Which one?
The x minus 2.
Yes, that's what I... This one?
No, the bottom one.
It's a minus.
By a. Like x minus 2.
You said x cannot
Oh, yeah, plus 2. Oh, you mean these two, right? Yeah, thank you. Yes, so 2. So x cannot be 2. Thank you. Okay, so in this case, we would have gotten the equation, the graph of a linear function with y-intercept at 1 and rise over run 1, you know, like this. That'll be the graph of this linear function. That's if we were only given y equals x plus 1. However, this x plus 1, think of this function coming from another function. In other words, we are going to consider in a way the dark past of this x plus 1. What is that dark past? Well, what happened here? We cancel x minus 2 over x minus 2. But that x minus 2 represented a discontinuity at x equals 2. So the new function, the simplified function, inherits that dark past, which in this case, it's going to be a hole right here. Whoops. All right, that hole right there. All right. And in this case, well, what kind of discontinuity here? Removable. Okay. Let's look at another example. So, f of x equals 1 over x squared for all values of x except equals to 0. Well, because observe the domain of that part of the piecewise function, and 1 whenever x equals to 0. Okay, what about the second statement right here? Let me highlight it. What is this trying to say? This really means that f of x, which is y, equals to 1 whenever x equals to 0. In other words, write it as an ordered pair, 0, 1. Okay? And let's draw the graph of this function. Well, so for a big reason, we cover almost a whole first chapter to review the parent graphs. So we have the graph of 1 over x squared, which looks like this. All right. In this case, the even power in the denominator make the two tails of the graph point towards the same infinity on both cases. But that's not the only thing we're graphing. We're also graphing this point in the middle of nowhere. That is the point 0, 1, which is this point right here. Okay. Let's observe the limit. So what's the limit from the left? Where is that going to? Positive infinity. What about the limit from the right? Do the limits agree to the same value? I mean, even though the limit will not exist because it's going to infinity. Yes, that is true, but we call it infinity. However, when limits, we call it D and E. That's because they point towards different infinities. In this case, the limit exists, which is infinity. That is limit f of x equals infinity, x approaching 0. Now, what is f of 0? What is the function evaluated at 0? 1. Okay. Is the function, the value of the function, the same as the value of the limit? So that's why this is discontinuous. It's a discontinuous function because those two quantities disagree. Now, observing the graph, what kind of discontinuity do we have? Infinite, yep, infinite discontinuity. Okay, let's do one more. And this is going to take us back to the same example in part A, x squared minus x minus 2 over x squared. I'm not going to do the whole work of factoring and reducing. I'm just going to use the result from part A. And I'm going to draw the graph. I'm going to draw the graph of that. After simplifying, we got y equals x, was that plus 1, right? And in this case, 1, 2, 3, 1, 2, 3, 4. That's 1. And we got that whole over here. All right. But also, we have more information that we didn't have before. We have this 1 whenever x equals to 2. That means exactly the point 2, 1. Okay, let's draw the point 2, 1. Okay, let's observe the graph and let's find the limit. Okay, limit x approaches 2 of f of x. What's the limit? 3, right? Now, what's the limit? Oh no, not the limit. Actually, what is f of 2? 1. Do these two quantities agree?
No.
Do we have a continuous function? No. Okay. No, it's not DNE. So separately, the limit exists and the function is defined. However, because the two values disagree, our conclusion here is that the function is not continuous, or it's discontinuous at x equals to 2. Now, question for everyone. How would you fix this given piecewise defined function so that it defines a continuous function? What would you change here to make it continuous? Change this one into a 3. Yep, change this one into a 3 and instead graph the point 2, 3. And this point 2, 3, oh, we'll fill in this hole right here, making it a continuous function. And in this case, we would check with the definition of continuity that the limit on both sides, which agree to the same value, also agrees with the value of the function. So we would have a continuous function. Do you see the difference here between how is it a discontinuous and how it is continuous? Okay, let's see what's next over here. Actually, for whatever reason, this PDF file went crazy, and I have information that we're not going to need. Like this example, we don't need it. This definition right here, well, it's continuity from the side, so it's continuity from the right when the limit from the right is exactly the same as the value of the function, or continuous from the left when the value the limit from the left is exactly the value of the function. So let me go back to that big and crazy graph right here. Well, let's see if we can have an example of those. So I'm going to focus on x equals to 3, and I'm going to find continuity in this case from the left. So let's see, limit f of x as x approaches 3 from the left. What's the limit? -2? All right. Oops. Now, what is f of 3? Also -2, isn't it? So in this case, this crazy looking function is continuous from the left for x equal to 3. So that's this theorem in action. Well, unfortunately for this graph, we don't have anything to compare it with something from the right, okay? But it would be the same idea, but now comparing with a side limit, but this time coming from the right. So, okay, let's go back and define the different continuous functions. And well, this should be, I mean, this should be the picture coming back from pre-calculus, you know. Polynomials, okay, but polynomials are continuous everywhere because for polynomials we don't have any gaps, any asymptotes, or any holes, etc. Yes?
What type of function are you with C?
Oh, yes. This one, removable. Yep, removable.
So on the examples, you want us to identify which one it would be?
Yes. So, continuous functions. Well, we know polynomial functions are continuous everywhere. I mean, we don't have any asymptotes, we don't have anything weird. What else? Inverse trigonometric functions. Well, not continuous everywhere. We have some restrictions. The only one that is continuous for all real numbers is the inverse tangent function. And what else? Trigonometric functions, only sine and cosine are defined for all real numbers. The other ones, such as tangent, cotangent, secant, and cosecant, they have discontinuities in the form of vertical asymptotes, and those are called, again, infinite discontinuities. And rational functions, well, just want to make sure that the denominator is not 0. Other than that, the functions are continuous on the domain of those functions, except, well, for the values that make them 0. Root functions, you might remember we discussed the two different root functions. Number one, the root functions that have an index being odd and the index being even. And for the index being even, those have restrictions. We cannot find even roots of negative values because those are going to take us to the complex number field, and well, we don't want to go through that. So on the other hand, the roots having odd radical, or rather odd indices, those are defined for all real numbers. Exponential numbers, they really don't have any restrictions at all, plugging in your favorite value for an exponential function. But logarithmic functions, well, the basic one like ln or log x, it's not defined for 0 and it's not defined for negative values, so only positive values. And well, the next theorem is, well, when you have two continuous functions, so if you add them or subtract them, multiply by a constant, multiply the functions or divide the functions, of course, as long as g is not 0, because that'll be undefined. The continuity, it's still there. The continuity doesn't change when you add subtract, multiply, divide, whatever you do with those functions, we still have a continuous function. And well, so actually, this example number 2, this should have been in the previous section, not in this section. So example number 3. So let's determine where the following functions are continuous. So let's look at the first example. So we have ln of x plus inverse tangent and divided by x squared plus 1. So number 1, what do we have to do in this case? We need to look at every piece of the function individually and then put everything together. Alright, so number 1, ln x. What's the domain of ln x function? Is it defined for all real numbers? What's the domain then? 0 to infinity. So we already have some restrictions, right? Okay. What about inverse tangent? What's the domain of the inverse tangent function? Well, that'll be the range. Well, this one I'm going to give it away. So the graph of inverse tangent looks like this, with horizontal asymptotes at negative pi over 2 and pi over 2. But in this case, we don't care about the range right now. We care about the domain. And well, in this case, it's all real numbers. That is negative infinity to positive infinity. And last but not least, what's x squared plus 1's domain? This is a polynomial. The domain of a polynomial, a polynomial is defined for all x, right? Negative infinity to positive infinity. Okay, well, putting these together, it's continuous on its domain. And yes, the domain of the arctan is all real numbers. The domain of the x squared plus 1 is also all real numbers. However, the restriction comes from the natural log function, which in this case is continuous on 0 to infinity. Okay? So what are we doing when it comes to finding continuity? We are finding the domain of the function. But did we just rephrase this and say, well, instead of saying the domain of this function is boom, whatever that is, we're saying the function is continuous on this interval, the same interval as it is defined in its domain. All right? Okay, so let's observe, let's analyze a piecewise defined function. Well, what do we do here? So let's see if this function is continuous, and in fact, we're going to look at two cases. The one case, we need to check whether the function is continuous at 0 and whether the function is continuous at pi. Alright? So two cases. Number one, let's do case 1. Let's do limit. Okay, let's check the continuity at 0. Well, a function is continuous whenever both sides of the limit will agree to the same value of the function here. So let's see. Number one, we need to set this limit x, or rather f of x approaches 0 from the left, limit f of x approaches 0 from the right. Now, our center for now is the number 0. From the left of 0, we're going to define the piece x over x minus 3. However, from the right, we are going to define the sine function. Now, let's see if these limits agree. Okay, so that's going to be 0 over 0 minus 3. Well, what's 0 over 0 minus 3? Isn't it 0? And what sine of 0? So we have an agreement here, right? And in fact, evaluate the function separately, we should get the same result. Let's see if it is the same case on the other side. That is, limit f of x equals limit f of x whenever x approaches this time the other center, which in this case is pi from the left, pi from the right. And let's check. So number one, limit sine x, limit e to the 1 over x, x approaching pi from the left, from the right. Well, what is sine of pi again? 0. What is e to the 1 over pi? Well, whatever that is, we don't care. What we care is whether we have an agreement on both of these limits. Do we have it? Is it continuous at x equals to pi then? Is it continuous at x equals to 0? Conclusion. F of x is continuous for all x except at x equals to pi. All right. So we're like finding the domain of the function, if we will, you know. But in this case, we're giving it a new name. We're giving it the name of continuity this time. All right. And in fact, we're using different notation. We're using the limit notation to basically say the same thing. But the reason why we're doing this is because now pretty soon we're going to define the derivative, and this derivative relies on the concept of the limit, which also relies on the concept of continuity. We're going to put everything together to finally get to that idea. Okay, what's next? Well, the very last couple of examples. I'm not sure if we're gonna have the time to cover this example number 4. I might want to go back to this next time. However, I've just realized I forgot a very important topic from the previous handout, and I have it here. It's the squeeze theorem. I totally forgot about this page. Well, so the squeeze theorem is a very, very powerful tool to compute limits that we wouldn't otherwise be able to compute with the techniques that we have so far. Well, what is that squeeze? Sometimes we call the squeeze theorem, we call it the sandwich theorem. Well, I think I misspelled it. Yeah, sandwich theorem. You'll see why. So, we have three functions, f of x, g of x, and h of x. Well, so the idea is that we want to find the limit of the g of x function. That with the techniques that we have so far, we can't. But we're going to use the limits on the sides for the f and h, you know. So, let me do the graph. So I'm gonna have some random function, g of x. Okay, so this is g of x, or let me make something different here. So this crazy function will be g of x, and let me highlight this function g of x so you can see, so you can relate it to. And then we're gonna have another function, f of x and h of x. So this f of x will be this function right here, and this h of x will be this other function. So now check this picture. Doesn't that look like a sandwich of functions? We have the red and the yellow one are the breads of the functions in the breadth of the sandwich, and the function in blue are whatever topics you want inside of the sandwich, right? But in this case, we also call it the squeeze theorem because these two functions, the yellow one and the red one, are squeezing the function in blue. And the idea is that whatever limit is for f of x and h of x will be the same for the function in the center that we want to do. So let's do one quick example on how to find, or actually how to show that limit of x squared sine of 1 over x as x approaches 0 equals to 0. Well, so if we try direct substitution, that'll be 0 squared times sine of 1 over 0. But do you see the issue here? What's 1 over 0? It's undefined for now. It's undefined, but limit-wise, well, we would need to look at the 1 over x portion. The 1 over x portion. Okay, what's the limit from the left? Negative. What's the limit from the right? Do we have an agreement with the limits for plain vanilla 0? Oh, wait, without the squeezing. Do we have an agreement here? So no, because in this case this is negative infinity, this is positive infinity. We're going to totally different values in this case. So it's D and E. Well, but they're giving us the answer. They're telling us it's 0. How are we going to do that? Well, we're going to use the squeeze theorem. Now, we're going to start with the trigonometric function. Number 1, what's the range of the sine function? Minus 1 to 1. Okay. So, one way to write a function in its range is to write down sine 1 over x. This means this is valid between negative 1 and positive 1. That's one way to represent the range of a function, by writing it as an inequality. And this range, negative 1 to 1, it's the same range of all sine functions, regardless of what we have in the angle. All right, now we're going to manipulate this three-sided inequality. We want to make sure that the term in the middle looks exactly like the limit we want to compute. Well, what do we need in the middle of the sandwich so it looks like the actual limit? What would you do on the three sides of the inequality to accomplish that? So when we compare these two, what's missing?
X squared.
So what would we do on the three sides of this inequality? Multiply by x squared. All right. Well, negative 1 times x squared, that's negative x squared, less than or equal x squared, sine 1 over x, less than or equal 1 times x squared, that's x squared. Well, let's compare. If the expression in the middle matching the limit we want to compute now? Is there anything else that we need to do? So we're done with that part. So now we need to find the limit on the three sides, x approaching 0. That is limit negative x squared as x approaches 0 less than or equal limit x squared sine 1 over x, x approaching 0 less than or equal limit x squared, x approaching 0. Now again, well, we got the original limit. We cannot compute that. That's fine, because we can compute the limits on the left and on the right. So what's the limit on the left? Negative 0 squared, isn't that 0? Times limit x approaching 0, x squared sine 1 over x. What's the limit of x squared as x approaches 0? Isn't it 0? All right. Now the question here is where the squeeze comes into play. Something that is greater than or equal to 0 and less than or equal to 0 means equals to 0. All right? And we just proved the limit. Well, in some cases you will be asked to prove. In some cases you will be asked to compute. Either way, this is the work that has to be shown.